Welcome everyone. During this lecture, we'll introduce Hooke's law, the work done by a spring, the work done by gravity, the potential energy of a spring, the potential energy of gravity. We'll also introduce the conservation of energy theorem, and then we'll explore a conservation of energy theorem application. Let's begin by introducing Hooke's law. Hooke's law establishes the relationship between the force that is applied onto a spring versus the amount of compression or elongation that the spring is experiencing. So let's introduce a spring into our consideration. This is a typical diagram of a spring. We're showing the spring at its relaxed state. In other words, the spring is not being compressed and it is not being elongated at this location. So this spring is relaxed, and the location where the spring is relaxed is identified along the x-axis as x equals 0. The question now is what happens when the spring is either compressed towards the left in this case or elongated towards the right. Well, in this diagram we're showing someone pulling the spring towards the right, and that person is applying a force F that again is directed towards the right. As a result, the spring is elongated by an amount that we've declared as x. The question is, what is the relationship between the elongation and the force that's applied? Well, we have a general idea. We know that the more elongation that is impressed upon the spring, the greater the required force. So again, the more force we apply, the greater the elongation will be. And the same thing works in the opposite direction. In other words, if we apply a certain amount of force towards the left, that will result in a certain amount of compression in the spring. If we apply greater force, there will be greater compression. And so what is the relationship between the force and the elongation, which is x? The relationship looks like this. The force that's applied by the spring is simply denoted as minus k times x. Now k is called the spring constant. And it's a measure of the relative stiffness that's associated with the spring. So we can think of it as the spring's stiffness. The units for K are just newtons per meter. In other words, the constant, or the spring constant, tells us exactly how many meters of elongation the spring will experience versus the amount of force that's applied in newtons. Let's now discuss the significance of the negative sign in front of kx. The negative sign is there to remind us that when we apply a force towards the right, the spring in this case will react by applying a reaction force that's directed towards the left. And so when x is positive, as is the case in this diagram, the force that the spring will apply will be negative because the spring will pull us back towards the left. On the other hand, if x is negative, which means the spring is being compressed, we will have to apply a force that's directed towards the left. However, the spring will react by pushing our hand against, or pushing against our hand towards the right. And in that case, the force is positive. So again, when x is negative, the force is positive. When x is positive, the force is negative. And that is resolved through the introduction of this negative sign. When we use this equation, however, we disregard the negative sign. We only use it in relation to the magnitude that is derived from it. We will now apply Hooke's law within the following example. In this example, a 12 kilogram object is suspended vertically by a spring causing the spring to extend a distance of 4 centimeters beyond its point of equilibrium as shown below. Determine the spring constant K. First of all, we have depicted the spring at its relaxed state. In other words, where the spring is relaxed is always declared as x equals 0. In this diagram, we show that the spring has been elongated because it needs to support a 12 kilogram mass. And clearly, the elongation is 4 centimeters beyond the point of equilibrium. We'll begin to analyze this problem by constructing a free body diagram on the block. Of course, we have a 12 kilogram block, and 12 kilogram block has a weight, which we'll represent as follows. And that weight equals 117.6 newtons. At the same time, the block is being supported by the spring, and the spring is applying an upward force, which we'll label as F sub s. The block is in a state of static equilibrium, so there is no acceleration, and according to Newton's second law, the sum of the forces in the y will either equal 0, ma, or minus ma. Since there's no acceleration noted within our free body diagram, our choice, of course, is 0, which leads us to the sum of the forces in the y equals 0. There are two forces within this diagram directed along the y direction, and therefore we'll extend 2 fingers from the summation. We'll introduce the spring force as F sub s, and it's positive. The weight, of course, is directed downwards, so it's introduced as a negative. We'll transfer the weight to the other side. And the force of the spring, of course, in this case will just equal the weight, which equals 117.6 newtons. Now, in order to determine the spring constant, we could take advantage of Hooke's law. Note that Hooke's law establishes the relationship for the force of the spring equaling K times X. And as I mentioned before, we're going to disregard the negative. It's only there to remind us that the spring opposes the elongation or compression. But when we use this equation, we only introduce it as Kx, not negative Kx, within our calculations. So according to Hooke's law, once again, the magnitude of the spring force is just given by Kx, and I'll introduce absolute value signs, which means that if x is negative, we'll disregard the negative. The force of the spring was determined to equal 117.6. That'll equal K. The elongation in this case is 4 centimeters. We have to introduce that, of course, in meters. So 4 centimeters equals 0.04 meters. And from that, we can calculate the value for K. The value is 2940, and the units are newtons per meter. We will now introduce the equation for the work done by a spring. The work done by a spring equals 1/2 times the spring constant times the initial position squared minus 1/2 times the spring constant times the final position squared. This is a very important equation that we will be using throughout this chapter as well as future chapters. Let's apply this equation conceptually to the example that we just looked at. In this example, the initial position would be entered as 0 because the spring is initially relaxed, and the final position would be entered in as x equals 0.04 because the spring is extended 4 centimeters beyond its relaxed state. We will now apply this equation within the following example. In this example, a 5 kilogram object initially at rest is launched by a horizontal spring with a spring constant of K equals 50 newtons per meter. If the spring is initially compressed a distance of 12 centimeters from equilibrium, determine the object's launch velocity at the spring's point of equilibrium. The first thing we note is the representation of the spring in its relaxed state, and the position where the spring is relaxed is always designated as x equals 0. Next, we have compressed the spring by a distance of 12 centimeters, and of course there's a block attached to it, and when we release this block, the spring exerts a force that's directed towards the right and causes this block to accelerate and end up with a final velocity that we're noting as Vf at the point of equilibrium. We need to determine this final velocity. Let's begin by drawing a free body diagram on the block. This is a 5 kilogram block. And we notice that the spring is pushing the block towards the right with a force that we will label as F sub S. The block has a weight, which we will label as W. Of course, that equals M times G, which equals 49 newtons. And there's also a normal force directed upward, and because of this force that's exerted by the spring, the block will experience an acceleration toward the right. In order to determine this final velocity, we're going to apply the work energy theorem. Of course, the work energy theorem states that the net work equals 1/2 mv final squared minus 1/2 mv initial squared. In this case, we have 3 forces that should be considered, and therefore we're going to extend 3 fingers from the W net equation. We have to consider the work done by the spring plus the work done by gravity plus the work done by the normal force. We will now represent the relationship between the various forces and the resulting displacement. Of course, the spring applies a force towards the right, and the displacement is directed towards the right. So the spring is definitely doing work because the angle between the force and the displacement is 0. The work done by gravity is a result of the force of gravity, which of course is the weight, and the weight is directed downward. The displacement is directed towards the right, and the two of them form a 90-degree angle, and therefore the work done by gravity is 0 because the cosine of 90, as we've discussed earlier, equals 0. Likewise, the direction of the normal force is upward. And the displacement is directed towards the right. The angle between them is also 90 degrees, which means the work done by the normal also equals 0. And so the equation reduces to the following. The work done by the spring just equals 1/2 mvf squared minus 1/2 mv initial squared. Let's also note that the object begins with a velocity of 0. It starts from rest, so this term also disappears. In order to determine the work done by a spring, we will rely upon the equation that we discussed a few moments ago. Here's the equation, and we're now going to apply it. So again, the work done by a spring is given as 1/2 kx initial squared minus 1/2 kx final squared, and we'll introduce that into our equation. So this just becomes 1/2 kx initial squared minus 1/2 kx final squared. That is the work done by a spring, and on the other side we only have 1/2 mvf squared remaining. Let's consider the spring's initial position as well as its final position by referring to our diagram. As we can see, the spring is initially located at x equals -12 centimeters, and the final location for the spring is x equals 0 because the spring, of course, reaches its point of equilibrium. And so the second term goes to 0 because the final spring location is x equals 0. So the equation becomes 1/2 times 50 times the initial position is entered as 0.12 meters, right? 12 centimeters equals 0.12 meters. Notice that I disregarded the negative sign because we're going to square that term. And when you square a negative, it yields a positive result. Also, the 50 came from the fact that the spring constant equals 50 newtons per meter. That will equal 1/2. The mass of the object is 5 kilograms, and we're trying to solve for the final velocity, and you can see that this is a relatively simple process. First of all, we can note that the 1/2 cancels because there's a 1/2 attached to both of these terms. Next, the left-hand side equals 0.72, and on the right-hand side we have 5 VF squared. We'll divide both sides by 5, and that yields 0.144 equals VF squared, and finally V final just equals the square root of that result, which equals 0.3795 meters per second. We will now introduce the equation for the work done by gravity. Let's imagine that we have an object that's located at a certain elevation above some reference point. That elevation will be denoted as y initial. Sometime later, let's imagine that the object descends to a lower elevation, and we'll designate that elevation as y final. The question now is how much work was done by gravity? In order to answer that, let's construct a free body diagram on the object. Well, gravity is applying a force, and of course the force of gravity is called the weight. So there's the weight of the object. The weight of the object, of course, just equals the mass of the object times gravitational acceleration. And the object has undergone a displacement of y initial minus y final. And so the work done by gravity, of course, would equal the force of gravity times the displacement times the cosine of the angle between the force and the displacement. As we noted many times before, the force of gravity is just the weight. And in this case, the displacement is just y initial minus y final. We can note that this equals delta x. This is the distance that the block has traveled under the effect of gravity. It started at y initial, ended up at y final. That is a representation of the displacement. So the force of gravity, which is weight, could be represented by this arrow. The displacement is represented by this arrow, and of course the angle between these two vectors is 0 degrees. So this equation just becomes the weight times delta x, which again we noted delta x just equals y initial minus y final, and the angle between them is 0 degrees, which of course the cosine of 0 equals 1. So we can represent this as, now the weight equals mass times gravity times y initial minus y final times 1. This equation just becomes mgy initial minus mgy final, and that is the equation that represents the work done by gravity. We obtained this result by distributing mg into our parentheses. We will now introduce the definition of potential energy. There are a variety of circumstances under which an object is positioned such that it gains the ability to do work. Under such circumstances, the object is said to possess potential energy. Now, one way to position an object in such a way as to enable it to do work is to attach the object to a spring. And so if this location corresponds to the spring's relaxed state, if we attach a block to that spring and compress it by an amount that we'll note x as x initial, by virtue of the block's connection to the spring, this block now has the ability to do work at a later time. Therefore, this block has potential energy. And that is due to the compression in the spring. So how can we quantify the amount of energy that this block possesses at this location relative to the point of equilibrium for the spring? Well, it turns out that the amount of potential energy possessed by the block is directly connected to the amount of work that the spring can do on the block as it travels from x initial to its final position, which is 0. Now, according to the work done by a spring equation that we're looking at right here, if we allow the spring to do work on the block until the spring reaches its point of equilibrium, xf under these circumstances equals 0, and therefore the work done by the spring will simply equal 1/2 k x initial squared. Therefore, 1/2 k x initial squared represents the potential energy that is contained within the spring. Therefore, the potential energy contained within a spring is given by one-half k x initial or x final, and because it could be x initial or x final, we'll just term it generally as 1/2 k x squared. Of course, k refers to the spring constant, and x refers to the compression or elongation. Of course, PES stands for the potential energy contained within a spring. There's another way to position an object such that it acquires the ability to do work at a later time. If we consider the block, which we evaluated earlier, and label its elevation as y above some reference location, we note that if this block is released, it has the capability of acquiring a lot of kinetic energy. By the time the block reaches this reference location, the gravitational pull of the Earth will accelerate it and create a velocity, and therefore the block has kinetic energy, and anything that has kinetic energy, of course, has the capability of doing work. Therefore, by virtue of this block's position, this block contains gravitational potential energy. So how do we quantify this energy? Well, it turns out that the amount of energy that this block contains is directly tied to the amount of work that gravity can perform on the block. So let's take a look at the work done by gravity equation. Here's the equation that represents the work done by gravity, and if we allow the object to descend to a final position of 0, in other words, we're going to allow it to reach the reference location, then y final just goes to 0, and the work done by gravity will just equal mg times y initial. This is precisely the amount of gravitational potential energy that is contained by the object. And so, the gravitational potential energy of a mass, which we'll term as m, located at an elevation of y above a reference location is given by PE sub g equals mgy. We will now introduce the conservation of energy theorem. This theorem states that when an object is subjected to the work of conservative forces exclusively, the object's total energy content will be conserved as it travels through its initial, intermediate, and final states. Now there's an inherent condition that's built into the conservation of energy theorem. Namely, the object must be subjected to the work of conservative forces exclusively. And in order to understand this condition, we will introduce the definition of a conservative force. A conservative force is any force such that when work is done against it, that work is stored as potential energy. We will now introduce the two primary conservative forces. Let's refer to our earlier example and imagine that our block starts at the spring's point of equilibrium. By doing work against the spring, in other words, by pushing the block toward the left against the spring, all of the work that we perform will be stored within the spring in the form of potential energy. Therefore, the force of a spring is considered to be conservative. Likewise, let's imagine that our block started its journey at the reference location, in other words, at ground level. If we now do work against gravity, in other words, do work in an upward direction which opposes the weight, all of the work that we do will be transformed into the block's gravitational potential energy. Therefore, the gravitational attraction of the Earth is also considered to be a conservative force. For these reasons, the two primary conservative forces are the force of a spring and the force of gravity, which of course is represented by the weight of an object. For our purposes, any other force will be considered as non-conservative. In nature. We will now introduce the two equations representing the conservation of energy theorem. The general equation looks like this. And here's what the equation tells us. It tells us that if we add an object's initial gravitational potential energy, its initial spring energy, and its initial kinetic energy, that sum will equal the sum of the object's final gravitational potential energy, final potential spring energy, as well as its kinetic energy. In other words, that energy will be the same between the initial, the intermediate, and the final position of the object. The working equation looks like this. And of course, all that we have done is we've introduced the expressions for the gravitational potential energy, the spring energy, and the kinetic energy representations. This is a very important theorem, so we will incorporate it within a box. As you can see, the conservation of energy theorem equations come with a warning. If non-conservative forces are present, the work done by these forces must equal 0. If that is not the case, then we must use the work energy theorem instead. We will now introduce an application of the conservation of energy theorem. In this example, a 150-gram ball, initially at rest, is launched vertically from ground level by a spring with a spring constant of K equals 250 newtons per meter, as shown below. If the spring is initially compressed a distance of 30 centimeters from equilibrium, determine the following by applying the conservation of energy theorem. And in part A, we would like to determine the ball's launch velocity at the spring's point of equilibrium. In this diagram, as you can see, the spring is located within a hole that has been dug beneath ground level, and of course ground level is indicated by the line that I'm tracing right now. So this line is ground level. Also, we can note that the spring is relaxed once it reaches ground level, and therefore ground level is labeled as x equals 0 in relation to our spring. Also, whenever the conservation of energy theorem is applied to a problem, we must always designate the lowest position as the zero height reference. The lowest position reached by the object is right here, and therefore this location is considered to be what we call the zero height reference. And normally what we do is we extend a line across the entire problem so that we have a common reference point, and once we extend that line we label it as the zero height reference. The value for y equals 0 at this location. So the y value for the ball is considered to be 0 at its starting point. As I noted, we would like to determine the ball's launch velocity at the spring's point of equilibrium. That launch velocity is represented in this portion of our diagram, and we will represent the velocity with an arrow, and we will label it as V final. We must now consider whether the conservation of energy theorem is applicable to this problem. And in order to make that determination, we have to determine whether this problem is conservative or not. So let's address this question. Is this problem conservative? Let's analyze the forces acting on the ball. Certainly the spring is acting on the ball, and we determine that the force of a spring is in fact conservative. The force of gravity is also affecting the ball. The force of gravity, of course, is the weight, and the weight is present throughout this ball's travels. And we also determined that weight is a conservative force. So far we're 2 for 2. Are there any other forces acting on this ball? And the answer is there are no other forces. Therefore, this problem is conservative, and we can apply the conservation of energy theorem. So again, in part A, we want to find V final at ground level. The conservation of energy theorem states that if we add the initial gravitational potential energy plus the spring energy plus the initial kinetic energy, that will equal the sum of all three components in relation to the final state. Next, we would like to determine the terms that have a value of 0. So we will pursue them from left to right. Is the first term equal to 0 or not? And remember, we're using this portion of our diagram to represent the initial state, and this portion of the diagram represents our final state for part A. As you can see, the ball is located at the 0 height reference, which means that its initial y value equals 0. Therefore, this term is eliminated. The second term is the spring energy term, and you can see that it is not equal to 0 because x represents the compression in the spring, and the spring is in fact initially compressed. This term represents the ball's initial kinetic energy. Now, since the ball starts from rest, it has no velocity, therefore the velocity is 0, and therefore the entire term equals 0. Let's look at the diagram that represents the final state of the ball. As you can see, this term does not equal 0 because the ball does have a height above the 0 height reference location. In other words, ground level is not considered to be 0. The starting point, or the lowest point in the problem, is considered to be the 0 height reference. Since the ball is above this reference, it has a height, and this term does not equal 0. This is the spring term. X final represents the final compression or elongation in the spring. However, the spring is not compressed and it's not elongated at this location. It is located at its 0 reference, and therefore it has no energy, and this term disappears. And finally, the 1/2 mvf squared term is not 0 because certainly the ball has velocity at this location where it's being launched. And so our guiding equation looks like this. Let's substitute in the values. So we have 1/2. K was given as 250, and the initial compression in the spring is 30 centimeters, which is entered as 0.3 meters. That'll equal the mass of the ball. Now note that 150 grams equals 0.15 kilograms. G, of course, equals 9.8, and the final elevation of the ball, as you can see, equals 0.3 meters, right? The ball is 30 centimeters above the zero height reference line. Therefore, its height is considered to be 30 centimeters, which will enter as 0.3 meters. The last term amounts to 1/2. The mass is 0.15, and you can see the only unknown is the final velocity. So using a calculator, we note that the left-hand side equals 11.25. This product turns out to equal 0.441, and on the end we have 0.075 V final squared. We'll subtract 0.441 from both sides, and that yields 10.81 on the right equals 0.075 VF on the right. I'm sorry, the 10.81, of course, is on the left. If we divide both sides by 0.075, we obtain 144.1 equals V final squared, and by taking the square root, V final equals 12 meters per second. Let's take a look at Part B. In Part B, we want to determine the maximum height reached by the ball above its initial position. This portion of the diagram represents the ball at its maximum height, and of course when we find the maximum height, it's the height between the zero reference and the ball at this location. It's not going to represent the distance between the ground and the ball, and that's okay. We know a thing or two about a ball at maximum height, namely, we know that the final velocity at maximum height equals 0. We also want to take note of the fact that the spring is relaxed when the ball reaches maximum height, and so we're going to apply the conservation of energy theorem, and we're going to consider this portion of the diagram as a representation of the initial state, and this portion of the diagram will represent the final state. And so in Part B, we want to find Y max, and we will apply the conservation of energy theorem. Here is the conservation of energy theorem, and we're going to relate it to our diagram, starting with whether we have an initial elevation. As we noted earlier, the ball has no elevation initially because it is located at the lowest position within the problem. It's sitting right on our zero reference height line, and that means that the height is 0. So the first term disappears. The second term needs to be evaluated. And as you can see, x does not equal 0 initially. X refers to the compression or elongation within the spring. As we can see, the spring is compressed initially, therefore x does not equal 0, and also x only equals 0 when the spring is relaxed. In this case, x equals 30 centimeters, which will enter in as 0.3. So the second term remains. The third term disappears because initially the ball has no velocity. It starts from rest. Certainly this term does not go to 0 because the ball has a height. In fact, it achieved its maximum height at this final juncture, and therefore this term is preserved. The spring is relaxed when the ball reaches maximum height. Let's take a look. As we noted earlier, when the ball reaches maximum height, the spring is relaxed, and therefore the spring term does disappear. And so we can zero this term out, and we can also zero out the kinetic energy term because at maximum height, the final velocity of the ball is 0. And so the guiding equation just looks like this. 1/2 k x initial squared will just equal mg y final. Let's substitute the proper values. Of course, k equals 250, and the initial compression, as we noted earlier, just equals 30 centimeters, which is entered as 0.3 meters. The mass of the object is 0.15, of course that's 0.15 kilograms. G equals 9.8, and the only thing that is unknown is y final. The left-hand side, through the use of a calculator, just equals 11.25, and on the right we have 1.47 y final. If we divide both sides by 1.47, the final height equals 7.653 meters, and that, of course, is the maximum height reached by the ball. In part C, we would like to determine the ball's velocity when it reaches a height of 4.5 meters. And so the ball is somewhere between its initial and final locations. The ball is roughly somewhere in between those two, and we need to determine its velocity. So we want to determine v final at y equals 4.5 meters. And to do so, we'll apply the conservation of energy theorem once again. Well, here is the conservation of energy theorem. And we've evaluated the initial state earlier and determined that this term disappears, as does the kinetic energy term. On the right-hand side now, the final elevation equals 4.5 meters, so certainly this term remains with us. The spring is relaxed at an elevation of 4.5 meters, right? Because the spring is only engaged during the first 30 centimeters of the ball's travels. Therefore, this term remains. The spring is relaxed when the ball reaches 4.5 meters. Therefore, this term disappears. And finally, the ball will have a final velocity because the only time it is at rest is at the beginning as well as when it reaches maximum height. So at 4.5 meters, we're not at maximum height, which means that this term will remain. Let's substitute the values. Of course, k for this problem was equal to 250. The initial compression, as we noted, equals 0.3. We're going to square that. The mass equals 0.15. G equals 9.8. And in part C, the maximum height equals 4.5 meters. I should say the height, not the maximum height, equals 4.5 meters. Plus 1/2. The mass equals 0.15. And we're trying to determine the final velocity. Once again, the left-hand side has already been calculated as 11.25. The first product on the right equals 6.615 plus 0.075 v final squared. We're going to subtract 6.615 from both sides, and that yields 4.635 equals 0.075 Vf squared. If we divide both sides by 0.075, we obtain 61.8 equals Vf squared, and if we take the square root of both sides, the final velocity at an elevation of 4.5 meters equals 7.861 meters per second. Finally, in part D of the problem, we want to determine the ball's kinetic energy when it reaches a height of 4.5 meters. And in order to make that determination, we just need to rely on the kinetic energy equation. In other words, kinetic energy is just defined as 1/2 mv squared. We've just determined the velocity at an elevation of 4.5 meters, and so we can obtain that result fairly easily. The mass, of course, is 0.15. The velocity we just determined equals 7.861. We will square that velocity, and as a result, the kinetic energy just equals 4.635 joules. And that completes this lecture.